All right, so here we're going to solve a real similar problem to the last one, but this is from the ULB textbook, not the SATIQ textbook. So it looks a little bit different, but basically what they ask us to determine is IL of t in this circuit. So they want us to find IL of t, and they basically give us a whole bunch of information about this circuit. They give us that Vs of t is basically 10 times the cosine, that's a cosine here, of 2 pi times 1 kilohertz times t. I guess I'll throw the hertz in there. Someone complained in 220 that I wasn't consistent with my units, and that's very true. I'm pretty lazy with the units sometimes, but bear with me. If that bothers you, you should also leave that as feedback, because I do look at feedback, and I always want to make my classes better. Okay, so R1, C1 equals C2. Those are both 10 microfarads. I do appreciate that the ULB textbook seems to use realistic values of components. The SATIQ textbook does not, and I don't love that. But okay, so L1, 1 millihenry here, and then L2 equals 3 millihenries, and then the mutual inductance M is half a millihenry. Okay, and lastly RL is 20 ohms. So that's all the given information. Okay, so what we need to do first is we need to convert this circuit over to the phasor domain. Shouldn't be too challenging here. Basically the phasor for Vs, we'll just call it, just draw it like a sine wave, just call it 10 angle 0, but note that this is a sine wave, okay, or a cosine, right? It's always going to be a sinusoid, but it is a cosine signal. So when we find our phasor for IL, which is what we're after, when we convert to IL of t to finish up the problem, we're going to have to take that into account, that it's a cosine. So just don't forget that. We can't let that slip by us, okay? R1 is just going to remain 5 ohms, of course. C1 has its own impedance. It's basically going to be 1 over J 2 pi 1K times 10 microfarads. I'm probably going to need some more space here. Then we have L1, which is 1 millihenry, so that's going to be J times 2 pi times 1K times 1 millihenry. Okay. And then, of course, we're going to have an induced voltage source from the current that's flowing in the second loop. Let's write those currents right now. Let's just call this one IL1 of t. Or let's just call them I1 and I2. Just call this one I1 of t and this one I2 of t. All right, I'm defining them in the same direction that they define them here. Maybe I should define them differently, just so that we can show you that it works regardless. Let's define this one going in this direction instead. All right. That's a bad idea. Sorry. I'd rather just keep it in the same direction as IL. Makes more sense. We're just going to confuse people if we don't. Okay. So let's keep that how it is. Of course, we know that the value of this dependent source is going to be the mutual inductance impedance, which we don't know yet. It's J 2 pi times 1K times M, which is 0.5 millihenries. And all that multiplied by the current that induced this voltage, which in this case is going to be I2. Okay. Here, this is time domain, of course. I'm writing it as a phasor here because we're in the phasor domain. We don't know the polarity yet. We're going to have to analyze the dot convention. Theoretically, since the currents are defined the same and the dots are the same as they were in this circuit, we should get the exact same polarity here, but we'll go through that exercise again anyways for practice. And so let's draw the second loop here. It's going to be an inductor with J times 2 pi times 1K times, what is the value of L2? It's 3 millihenries. We'll do all this math in a bit. This is going to be 1 over J 2 pi times 1K, also 10 microfarads. Both capacitors are the same size. Then we have a load impedance or a load resistance of 20 ohms. Okay. And then finally our source, that's going to be induced by I1. So that's going to be I1 multiplied by J 2 pi, 1K, 0.5 millihenries, okay? And so we need to determine the polarity of these voltage sources. Obviously, we need to plug in all these values, and then we can go ahead and solve this circuit. Let me go ahead and shrink this a little bit just to give us some more room. What we'll do here is we'll determine the polarity. We'll do this math, and then we'll move on. This video might actually be getting pretty long here, but let me try and do the polarity real quick. Actually, you know what? Let's just calculate these values real quick, and then in the next video, we'll determine the polarity of those sources. Okay, so let's go 1. I'm going to have to make this even smaller. Let's make it a little bit smaller, and then I'll make a copy of it, and I'll just paste it right here. Okay, that's definitely not what I wanted to do. And now they're too big. Okay, I'm struggling, guys. Okay. That's good. Copy. Paste. And this will be our final circuit here that we're going to solve. Okay. Now that this video has gotten too long, I'm just going to end it here, and I'll just do the calculations and the polarity in the next video. And if we have to stretch this into 3 videos, that's fine. But I'll do the calcs in this video, so we'll get rid of all these things that have to be calculated. We'll fill them in the next video as we calculate them. Oh, I guess I can leave the I1. I can leave the I2 here. And we'll go ahead and calculate those, and then we'll be back. You know what? I'll just calculate them off screen and I'll plug them in. That's even better. That's a good way to save time. I'm going to end this video here. We'll see you guys in the next video, and I'll have all these values plugged in. But what I won't have plugged in are the polarities, so that we can go through that dot convention exercise again. Okay? I'll end this video here. We'll see you guys in the next one.